I'm going to talk about what I know as the Birch-Stevens formula. And I don't know a reference for why this is called the Birch-Stevens formula. This is unfortunately just the name I know. As a reference for this formula and for the stuff I'm going to say, I can give this paper of Maser, Tate, and Teitelbaum. Let me make sure I spell this correctly. From 1986, p-adic analogs of the conjectures of Birch and Swinnerton Dyer, and this will be sections 7 and 8 in that paper. Is very short. These sections are very short. So the idea is that you can define this L function. So L S, so well, maybe I should say what F is. So here we're going to take F of Z to be some n from 1 to infinity of an e and z. This is going to be a weight to level n holomorphic cusp form. I'm not. Let me maybe say it's an eigenform. Let me say a new form. Just to be safe. And this L function, LSF, is going to be the sum n from 1 to infinity of an n to the s, and I should specify that this is going to be the arithmetic normalization. So when I say the arithmetic normalization, what I mean is that the functional equation goes between s and 2 minus s. In some other places in the course, in most other places in the course, we had a functional equation going between s and 1 minus s. But now I'm going to talk about L of 1, and it's going to mean the central point of this L function. It's not the edge of the critical strip, it's the middle of the critical strip when I talk about 1. So this is the normalization I'm using. And you can show that this is a Mellin transform. So this is the Mellin transform. So, well, okay, you've got this stuff in front. 2 pi to the s over gamma of s. And then it's going to be an integral from 0 to infinity f of it t to the s dt over t. And this calculation, basically you take this this form, you substitute in this definition, and then you just integrate, and you'll recognize the gamma function coming out. That's why there's this gamma function down here. This is very similar to a calculation that we did when we were talking about when we were first talking about convolutions and mentioned the Rankin-Selberg method. So you can view this in this way, at least in the region of absolute convergence. And then what happens is that you can extend this to the region where you don't have absolute convergence. And so this is going to be that you're going to get what? That this is this integral from 0, this will be from to I infinity, right? Or sorry, just to infinity. And then, so this central value is integral 0 to I infinity of 2 pi I f of w dw, right? So it's this modular symbol going from 0 to infinity. So you can view this as 0 infinity of f, right? So that's cool, and this just is a direct result of this. And then the Birch-Stevens formula. So this is not the Birch-Stevens formula. This is just this is just some fact about L functions of these things. It's sort of starting point, or one of the main points of Tate's thesis stuff, I guess. But the Birch-Stevens formula is this twisted version. So again, this is just what I know this as. I don't know a reference. I don't know the year or anything like this. But this is, if you define Ls f chi to be the sum n from 1 to infinity of an chi n over n to the s. And here chi is going to be primitive mod n, or mod, sorry, uppercase n, the level of your form, I believe. I don't know if you need to actually assume that. Maybe you don't, but anyway, this is the case that I'm going to work with. And then you have the following identity, which is that L1 f chi is equal to 1 over tau chi bar times the sum a in z mod n of chi a bar times, and now we've got this modular symbol, so here I'll write just the matrix and we'll understand that it, understand how this goes. So a, n, and then the stars here just make it an element of SL2Z, and then here you have f. And so this is saying, the path from whatever I infinity to gamma I infinity. So this is, say, this integral from I infinity to a over n, if you like. And then by the Manning-Drinfeld theorem, this is some rational combination of the periods of f, right? So the proof of this is just substituting in the this expression for f, and then just rearranging things, recognizing Gauss sums, etc. It's totally straightforward and elementary. So you can find a proof, say, in Maser-Tate Teitelbaum. Okay, so this is an example of another reason why you might care about modular symbols, because if you want to understand central values of L functions, well, if you know what these modular symbols look like, say you know something about the statistics, then you can ask about how they're likely to combine and get statistics on central values. So there are a lot of reasons to care about modular symbols, and this is one of them.